Chapter 5, Experiments. This is going to be very useful and practical chapter summary. We will learn about A/B testing, which is the bedrock of running experiments in production or experiments on your users so that you can make data-driven decisions. So that's randomized control trials or A/B testing. We will learn about why it's very difficult to have perfect experiments and learn about situations where we can't do A/B testing like diff and diff analysis. We learn about using another technique called regression discontinuity estimators. Find out what is the endogeneity problem in demand analysis and how it's all related to running experiments and finding out causation. So in essence, we're finding out causation when we run experiments. We learn about the role of instrumental variables and how we, with the technique of two-stage least square, a new algorithm, this is the 13th algorithm in this book, can we identify the instrumental variables and also find out their role and conclude with advanced topics. So there is a lot to cover. But in one line summary, if I were to summarize this chapter, it's basically this. Experiments or A/B testing is a way to make data-driven decisions. It's a very systematic way to make data-driven decisions to really find out what's working for your customers, for your users, and what's not working for them. So you can use a statistical technique with randomized control trials and design and use the power of A/B testing to actually know a causal link between some things. Like saying, hey, if I increase the price of my product, it will actually sell more or not sell more, could be one such A/B test. If you change the logo of your website from a blue color to red color and maybe there is a positive increase in engagement on your website users. That's an experiment. If you treat someone and certain groups of people with a new drug and they get really better in terms of not having a specific disease that your drug cures, and you compare that with someone who didn't get the drug and they get a statistically significant lift, then it's an experiment. So those are examples of experiments, and we're going to learn more. But in one line, experiments or A/B testing is a very powerful way to make data-driven decisions to find out what works and what doesn't work. So let's take an example. Yeah, I have two examples here, the first image on the top and the second image at the bottom. In this first image, it's let's say we have a pool of patients and it's a hospital. And for a certain group, you call it the A group or the treatment group. You give them some special treatment, right? Let's say you wash your hands as a doctor 3 times instead of 2 times for a specific routine. And here you wash it just 1 time in control group. So there is this difference, an explicit change in how you treat your treatment group or certain parts of your group and certain parts of your group in control. And you want to just say, hey, find out, is there a difference in overall result of recovery if I were to wash my hands 3 times as a doctor at a specific set of intervals, and there's less issues with the patients, and versus just continue doing what you were doing, which was washing 1 time. So you can divide this group into 2 and then check and compare the results between your treatment group and your control group. Similarly, and so that's an A/B test or a randomized control trial. So the randomized part here is that you randomly divide your patient pool into these 2 groups. That's an important aspect. Another example, let's say you are a consumer website like Amazon. You have visitors who are buyers who are trying to come to your website. You can do the same. You can divide them randomly into an A group and a B group, or a treatment group and a control group. Let's say for some of them, you know, by default you used to show them this red box at the top right of your website. But now you want to try out if a blue box has a better engagement, you know. So then you find out and you say, hey, blue box has a 17% lift in, let's say, shoppers adding to the cart versus the red box, which has 24%. So now you just ran an experiment that says, hey, this is the clear winner because it has a much higher lift. So those are two examples that builds an intuition as to how you randomly create segments, an A segment and a B segment, or a treatment segment and a control segment, and then you compare from a control segment what's the lift or what's the degradation in your treatment segment. Yeah, so that's the intuition. And the main reason why we want to do this randomization is we want to move from just identifying correlation to actually getting to causation. And we can do causal analysis in two different ways. By this experimentation or A/B testing that we just went through, which is also called as randomized controlled trials, where we explicitly manipulate the treatment group, right? We explicitly manipulated how this treatment group receives a drug, right? We gave them a drug. So it's an intervention. Or in this group, we explicitly changed the look and feel to a blue box from the default red box. So experimentation or randomized control trials is one way in which you can get to causal analysis and conclusion. The other one is observational studies. Again, in observational studies, the main difference is you don't make any changes. You simply observe in a phenomena that's happening, right? It has strong assumptions because you have to figure out a way to remove confounding influences, right? And be able to control for them to actually have this causal link. But these are two ways. In this chapter, the primary focus is on experimentation. The next chapter is going to be on observational studies and how we do that, right? And how we control for it. And the causal analysis has two parts. The question that's being asked, and you see what is the change in this treatment group when you give this new drug. And then you see that the intervention caused this outcome. That's the factual outcome, a causal question. Like, hey, if I gave them this new drug, what was the impact? Or if I show them this blue box, what was the lift in purchases? So that's the factual outcome. And then the second one is the factual outcome or the manipulation on the treatment. And the second one is, again, answering what if you didn't do this? What if you didn't give this treatment? You just kept them as is the control, or kept the red box, the default as is. That's the counterfactual outcome, which is what is it the outcome if, you know, the absence of that manipulation that you did, right? So that's the counterfactual outcome of what is unobserved. It tries to answer the what if, right? And that's the basis of causal analysis, right? So we gave this example, but in a sense, this whole foundation is built on this randomization. That's the key takeaway. If you don't randomly break down these two groups, then there's a problem, because it uses this key statistical property or independence to actually lead to this causal conclusion. Without randomization, this whole setup is broken. And so this is the summary, right? You are able to statistically get to causal outcome and definitively say that this blue box is significantly poor compared to this red box by, let's say, this 7 percentage points, right? So that's the causal link. It's, hey, adding this blue box given all else equal, which is what this randomization provides. The independence is provided by that. And so that is what you use for A/B testing. So that's the intuition. We went through the nitty-gritty details as well. Now let's look at why this is hard, right? These kind of experiment setups are hard because of these 11 reasons listed out here. You know, you want to test the right set of things. If you test for something that is a weak, test because you're not asking the right question, or not really asking what changes in this previous example, we were asking, hey, what is the lift in this purchases? So that's a good question. But if you don't test for the right things, then you may be misled to answering wrong things. You want to make sure that there's good sample size so that you can compare apples to apples. You want to make sure that data is reliable. You want to get the hypothesis right. There's several things. You want to schedule the test correctly. You want to nail the duration in which, how long do you run this test? You don't want to make changes mid-flight. There's also issues around customers, like they'll get confused when certain segments of your users see blue and certain see red. And there could be lots of tests going on. And so there's lots of areas why this is hard. In a sense, right, when you make small changes, let's say on a website, and you can see the randomization being used perfectly, then this is very much applicable. But remember, the preferences of the users change. Consumers can also intervene into your tests. Let's say you depend on your browser cookies to identify certain things for the user as to whether they are in treatment or control. Then let's say they clear or delete their cookies, then your whole test setup is broken. And there's this piece around how do you get this perfect randomization. If you don't get perfect randomization, this whole setup doesn't get independence between those observed treatment and control group, which leads to no direct causal link. And then there could be dependency between observations. So that's, it has to have independence as the criteria as we talked about. We talked about number of samples being small, the duration of tests, and so several reasons why designing a perfect experiment is rare. And so doing it well is an art and a science. And so you want to really perfect this if you run and make big business decisions from this. The other technique, which is diff and diff analysis. What if you can't run an experiment? What if you just can't run it because of, let's say, some legal reasons? Let's say you want to find out something about discrimination in certain segments, or you want to find out the impact of adding or reducing minimum wage, or certain ethical reasons why you don't want to run experiments, but you still want to find out what is the causal link, what's happening. And so that's where you use this technique called diff and diff analysis. When you do this when there's randomization is not possible. And these experiments are called near experiment designs. And there are two types, diff and diff, which is what we'll cover in this slide, and regression discontinuity, which we'll cover in the next slide. But these are alternate ways in which you can get to causation. But this has a very strong set of assumptions, right? So before we get into what is the assumption, let's understand what diff and diff is, right? So let's say this is the green line. Green line is, how before intervention and after intervention. Let's say you had an intervention where you started providing lunch in school, right? And you see that, hey, for this particular school, which is the green line, and there's also this other school, which is the red line, and you started providing lunch only for this school at this point. And what you saw is that after you started providing lunch, the test score started to increase, right? And then you can compare that to a school which doesn't have lunch provided. And then you see, hey, if I didn't provide lunch, I would still get this constant improvement that I see over time, but I get an extra intervention effect, right? So that's the observed outcome trend because of intervention, right? So that's a basic technique in which you can see like what's the extra lift, and you reduce the constant difference that you already get out of like a school that also doesn't provide lunch, right? So what's the big assumption here? The big assumption here is that whatever else is happening in this school is exactly happening in this school. We know that this is not for certainly, it's a very strong assumption because this is not true. There's so many things happening in the school with this red line, and that could be very different than what's happening in this green line. Maybe this school was on a track to constantly improve, or it was actually there's some other variable that's actually causing this change and not the lunch. So that's a big strong assumption. The other one is regression discontinuity. Let's say you want to find out the impact of, you're on Amazon and you want to find out like, hey, if I put a $75 limit as minimum limit before which you will not get free shipping, then what you do is you find out like, hey, at the 70, if I introduce the 75 limit, I suddenly see lots of people, buying goods. The volume just increases because of this, around this $75 mark. So that's the other technique, to find out using regression discontinuity estimators, to find out like what are those forcing variables around which there's a big change, right? So you can easily say, hey, this blue line would have continued to be this way if there was no treatment, but I added this intervention, the $75 limit, and now all of a sudden there's a lift in because of treatment. So, or you could say you're trying to find out, it's another example where you're trying to find out discrimination law for firms with greater than 15 employees, right? Again, you can't run A/B tests and discriminate people. That's just illegal, not ethical, right? But you can run a test that says, hey, free shipping over 75, or you want to try out 45 or $35 or $25, right? So you can find out what the lift is with and without, with using regression discontinuity estimators, right? And so the big assumption here is that if the thresholds were to move slightly, there would be a switch, right? So if you were to move from here to here, you will see that switch. But typically it's a continuous curve. But there is some aspect around introducing these artificial forcing variables or forcing functions that you can introduce in your products to test out the difference between the lift that you get. This new concept of endogeneity is an important one to learn. So let's say we observe a peak in the travel season where most of the airline tickets are booked, yeah? And we also see that they're also very expensive. Not only the tickets are booked, but they're also very expensive. So can one easily conclude that the tickets are booked because prices are high? Think about it. Can you conclude that the tickets are booked because the prices are high? This is the upward sloping demand curve. Demand curve is typically downward sloping, right? So it's true that both flights are booked and prices are high, but there is something else. There is a higher consumer demand that causes the flights to be booked, and the flight operators know this fact, and so they jack up the price. So there's this something internal that is already in the system that can be a better predictor. In general, endogeneity refers to the situation in which an explanatory variable, right, in this case prices, is correlated with the error term, right? In this case, you could say, hey, there's a higher demand, right? So when you have that, you can say that there is endogeneity, right? So in a sense, if your independent variable is being predicted by, let's say, two dependent variables, and if you can predict the error term with your dependent variable, right, then there is endogeneity. But if you cannot predict the error term with your dependent variables, then it is exogenous, right? So if it's not exogenous, it's endogenous, right? And so in essence, what we're trying to find out is there something else, right? So let's take an example to make it real. Let's say you're trying to predict wage of someone, the outcome, the independent variable, with this one dependent variable called, if they participated in the military, what's their wage, right? But you can also see that there could be one other variable, which is this person eligible to be drafted into the military, that causes them to be participating in the military. That's what causes the wage to go up. Then you can quickly see that there is this instrumental variable, IV, that causes this, right? So like the consumer demand example is the instrumental variable. So how do we solve for endogeneity? It's instrumented variable. Find out which are the instrumental variables that has a direct impact on the treatment that causes the outcome, but the instrumental variable has no connection directly to the outcome and has no connection to lurking or confounding variables, right? So if these things are true, meaning the instrumental variable, in this case, intent to treat a patient, that's another example, It's an instrumental variable. Like, do you have an intention to treat someone? Then you would find out whether they actually take the drug. You can't just say, hey, this person took the drug, and then they recovered. There could be this piece around like even screening out those people who you're going to treat. So the instrumental variable has a huge correlation to treatment, has no correlation to outcome, but treatment causes outcome, right? So the way you solve for this is you find out instrumental variables. And how you do that? You find out what are other things that explain these upstream variables that has a big impact on your treatment variable. And once you find that out, you can actually run this new technique called two-stage least square, which we're going to cover here. And the way you do that is you first find regression to establish that there is a correlation between draft eligibility and the military participation. So that's the stage one. You find this out. I know I'm hopping through different examples, but it's the same. Instrumental variable causes impact on the treatment causes the outcome. So you first find out this stage one, and to establish that there is a correlation. And the second stage, you find out this correlation, military participation and wage. Once you do that, you can also check that draft eligibility has no impact on wage, right? When you do that, you found this to be an instrumental variable. And this technique is called the two-stage least square technique. This is the new algorithm from this chapter. So far we've covered 12 algorithms. This is the 13th one. So this is two-stage least square. You quickly can find out what is this instrumental variable with this technique. With this, I'll conclude and share that this is just an overview of how experiments can be designed, what are alternate ways in which you can get to causal outcome if you can't run experiments. But there are lots of things, as we talked about in one other slide, where you have to really design experiments well. You have to make sure that the sample size is appropriate in both of these treatment and is very close to the control group. And you want to make sure that you run experiment in such a way that doesn't cause confusion on your customers. Like, let's say a customer is using your product. Sometimes they see the red box, sometimes they see the blue box, and then they're like, what's going on? This website is so jarring because you're running so many experiments and things are just moving around. They can get disoriented. And so you want to run tests. You want to make data-driven decisions, but also make sure that your product is not impacted. You want to make sure that you don't take wrong results, meaning you don't incorrectly conclude, and when there is, let's say, no statistical power or between in your tests, and you still say that this test is successful. So you want to make sure that your outcomes and success measures are not only defined before you run the test, but that you actually conclude in the right way. You want to make sure that your tests are actually run the way you want it to be run. And you want to define what the test is as to what is the causal link you want to test for. And you want to also know what is the short-term versus the long-term difference. It may be true that there is this causal link in the short term, but things change in the long run. So how do you make sure that you are testing for that and short-term impact versus long-term impact? So this is a very, very powerful area, experiment design, which will tell us what is the causal link and make decisions that are powerful and based on data. So that's the summary of this chapter. Thanks.